what I'm going to be talking to you today about is really, I think, a personal journey. It's about understanding the emotions that bind us, the kind of things that makes us tick. And of course, what you've just had, food, is one of those things. And of course, being with other people is another one of those. And the kind of things that have been going on in the background, the kind of cave art, which is one of the first things that people did. Why would people do that if there wasn't emotions involved in that? So art and science are linked, and art and emotions are, of course, very closely linked, but it's linked through this very special organ, the human brain. And that's really what my book is about. And my book is to understand how it is that we come to have these emotions. And if you think of emotions as molecules, if you then think about the atoms that make up that molecule, my contention, and one of the things I've been trying to argue in this book, is that pleasure and pain in as many forms is what makes up those emotions. So you've already seen the picture of the book, which came out earlier this year, which I've co-written with Helen Phillips. It really is a textbook, so it tries to come up with all the different forms, all the different ways that people have been thinking about emotions, and then try to weigh them up and try to make them accessible for an intelligent reader. Now, just taking recent events, the 9/11, things like Shakespeare or even Mo Farrow, those are the kinds of things that evoke emotions in us. And why is that? What is it about these kinds of events? What is it that the brain is doing when we get some kind of stimuli? We then do whatever it is that the brain is doing, and then we have some action at the end of it. And of course, that feeds back in perpetual feedback. So what is it then that the brain is doing? Well, let's start with the stimuli. So when you see something, and this is an artwork made by Annie Cattrall, who's here, of different irises, of different generations from the same family. Now, the interesting thing about the iris, of course, is it's the only part of the brain that you can see with the naked eye. But what happens then when light comes and it comes to the back of the brain, you then have to make meaning of that. And if that image that you're looking at is just a collection of black and white, then it can be quite difficult to make sense of that. Not many of you will be able to see what it is, but all I have to do is just show you this image. And then all of you will be able to see that there are, in fact, two little girls there. Now, you probably would have to be their father in order to really get emotionally detached to them. But yet, just having seen that there's two little girls will already have evoked some kind of affective reaction in you. And understanding that affective reaction, understanding what it happens when you have that reaction and what happens when you don't have it, when it goes wrong, is what my research and what this book is all about. And what I'm going to be talking to you today is slightly linked to this famous painting where there's a man being trepanned. I'm going to show you how it is that we can now stick electrodes into people and change who they are. Now, the one thing that we share these days is probably only the headgear as a neurosurgeon. But at the same time, this fascination with the body and the fascination and the understanding that we have these organs that are all electrically mediated, really. So you've all seen frogs where you stimulate them with electricity, and of course, if they were to stimulate that arm, that muscle would twitch and you would have some kind of movement. Now, the key insight here is that the brain is also electric. So when Walter Whitman talked about singing the body electric, these days really he should be talking about singing the mind electric, because all that happens in your brain is essentially electrically mediated. And so these days we have very expensive machines. This is an MRI scanner that a lot of you will already have been inside. When you put yourself inside of these, you can actually look at the organs as they come out. Here's a cross-section of 15 brains. One of the things to notice is that you probably can't tell which of them are women and which of them are men. It's very difficult, even for a trained neuroscientist, to tell any difference between the male and the female brain. But it's even harder to tell that one of these is actually a famous TV presenter. So what is it that makes these brains so alike, and what is it that happens as we experience the brain? So together with Annie Cattrall again, we got interested in thinking about what might happen if we had somebody lie in a scanner and have them see something, taste something, smell something, touch something, and hear something. So the 5 classical senses. And what I'm showing you here is is an animation, and mostly when people see this, they say, oh yes, you're Danish, Morten, aren't you? Hamlet, yes, yes. Alas, poor Yorick, I knew him so well. But the key thing here, of course, is to notice how these different blobs, which corresponds to the different kind of senses, where they are. And just to make it more easy for you, I've shown you now as a brain seen at the bottom from above, sort of if you were to look at me like this, looking that way. On the top, I would be looking from the side, and on the top right, I'll be looking straight at you. And in red is where you've got the visual areas. In blue is where you've got the touch areas. In dark blue is where you've got auditory and smell, and taste is the various shades of yellow and orange. And one of the things that happened when Annie and I made this piece of artwork, which I'll show you in a moment, which is called Sense, is that I started through the act of exploration and not exploitation, as I usually say, namely thinking about with Annie, what is it actually that's going on? Because of course one thing is sensing the world, another thing is making sense of the world, of actually emoting the world, of pulling things together. In the old days when you looked at maps, when you didn't know where things were, you said, here be dragons. And here be dragons in the brain, of course, is all the empty spaces that are in between, because of course that's where the information comes together, and that's really where the really interesting dragons are. Now here's the artwork that we made that Martin Kemp, who would have been here tonight had he not been otherwise detained, but this is an artwork that I think sort of is one of the first sculptures to actually reveal what it's like to be somebody experiencing something. But of course, the big question becomes, what is it actually like feeling something? Here's the map here, the dragons. And the dragons, of course, could be something like chocolate. Having chocolate is not just feeling that it's got that kind of texture, not just seeing that it's that kind of darkish thing, but it's actually having the experience of having eaten that chocolate. What about sex, though? Again, if you think about Freud, he contended that it was all about sex. And somebody then sketched this particular drawing, which, of course, tell you that it could be about sex, what it is that we're thinking about and feeling about. And then somebody like Magritte did a portrait of his patron, who was a very large hedonist, somebody who loved pleasure in all its many forms. And in fact, he forgot to draw the head. Or maybe, in fact, he didn't forget it. Maybe this was what actually drove him to that. Because, of course, the contention here is that in order to understand what it is that we are and what then goes wrong in mental illness, we would have to understand what pleasure is. Not just pleasure, but its flip side, the lack of pleasure, anhedonia. And understanding that would potentially give us a nice way into understanding how it is that we can treat mental illness. But in order, as I say, to understand that, we would have to understand how pleasure works. Now, this is a classic sort of pleasure cycle. I came to this gallery tonight feeling quite peckish. I was in pursuit of food. Had this had been another era, I would have spent a long time looking for food, killing it maybe, or even getting in. But I knew that Gary would come through for me and Robert, and so there was food. So my brain changed at some point, so I engaged with that reward. I had moments of high pleasure, and now I'm in the phase where if you ask me if I could have any more of this, I would probably say, no, I'm not sure I could have any more. So I'm sort of at the end of the satiation. I'm disengaging from the reward, although all it would take would really be for Gary to say to me, what about some chocolate, Morten? And then I would pull out my little extra dessert stomach, and I would probably say, yes, I could do, and we'll get back to that in a moment. But when you then think about these cycles, the reason why I disengage from that cycle is now I'm engaged in another cycle, namely talking to you, doing other things. And so you can think of all of these things that the brain do is about allocating resources at the right time. And when you think about that right time, that of course happens over seconds, minutes, hours, days, weeks, months, and even lifetimes. And with each of these, there are emotions and longer lasting emotions that are expression of who it is that we are. And when we talk about emotions, normally we talk about the self-reported ones over minutes, but of course their expression and autonomic changes. If a bear was to jump in and I get this kind of fright, that would show within seconds. But my mood swings would be something that would happen over months or weeks even. And so when you're interested in that, you can look in other animals, and many of my friends do that. You can look in rats, or you can look in monkeys. which I think are really important and exciting ways to look at that. But if you were interested in the human species, you would have to come to realize that what has happened to humans since we shared a common ancestor 100 million years ago is that our prefrontal cortices have grown substantially larger. So when you're looking for emotions and for pleasure in the human brain, you have to look at the front of the brain, just over the eyeballs. And this is an experiment where we looked at what happens when you take something like the dessert stomach phenomenon. We had people come to our scanner hungry, and we had made sure before they came that they liked both tomato juice and chocolate. Not at the same time, because of course that's not particularly nice, and there were no vodka with the tomato juice either. And so they were lying in our scanner. This was an MRI scanner. We gave them a little bit of 1.5 milliliters of tomato juice, then a rinse, and then 1.5 of the chocolate milk. We then did that for about 20 minutes, and people rated both of them very highly because they were hungry. Then we took them out of the scanner, sat them up, and asked them to drink as much tomato juice as they possibly could, and then some more. And the other half we asked to drink as much chocolate milk as they could. And then we put them back and did exactly what we did before. A little bit of tomato juice, a little bit of chocolate milk. And now if you've had a lot of chocolate milk, you no longer like the chocolate, and vice versa. And so we were looking for parts of your brain that were high to both of them initial, high to only the one that you hadn't been sated on, and low to the one you had been sated on. This phenomenon, which is called selective satiation, is something that is common across all of the pleasures. And when you look at that in the brain, you find that a part of the orbital frontal cortex seems to react maximally, suggesting that this really is the part of the brain that has to do with subjectively experiencing pleasure in the human brain. And so I wanted to look at that in its many forms. And of course, if you're interested in pleasure like I am, you would like to do a sex study. But unfortunately in Oxford, we don't do that. We close our eyes and think of England. So I had to rely on the Dutch. So a good friend of mine, Yannico Georgiadis, did one of the best studies that I know out there. It's the only study that I know where there can only be women in the study. I don't know whether you've seen the Woody Allen film where Woody's soon-to-be ex-wife looks at him in disgust. I think it was Mia Farrow, but I'm not sure it links to what had happened recently. She looks at him in disgust and says, "I faked all my orgasms." And Woody kind of pops up and said, "So did I." Now, I don't know about you, but for the rest of humanity, it's kind of hard for men to do that. So when Yannico wanted to look at the difference between faking an orgasm and having an orgasm in the scanner, he had to use only women. And so what I'm showing you here are images of the changes that happens when a woman has an orgasm compared to when she's faking one. And you might ask, how do they know? Now, I'm sworn to secrecy because when I did this as an after-dinner speech the other night, there were two young ladies that came up to me and said, "Please don't tell our husbands, please don't tell our husbands." But it turns out that there's a very good way of telling whether somebody has had an orgasm or not, and we can maybe take that for dessert. But just thinking about the pleasure cycle in terms of sex here, what I plotted on the top is that kind of classical thing where you have desire, arousal, you have a plateau phase, there might be an orgasm or there might not, and there's a refractory period. And what I've plotted below is basically the kinds of changes that happens in the brain. And so what is happening here is that the brain is running in different modes, if you like. And what is important here is the state change from when you go from having desire to arousal to plateau to orgasm and so on. So what is important is how the brain changes in terms of how it is that you change between these different modes of operation. Because of course it can happen that if you, and this we could do in Oxford, and don't ask me why, but if you can actually give people crystal meth, methamphetamine, in the scanner. And when you do that and you give it to drug-naive subjects, what you find is the whole pleasure network lights up like a Christmas tree. The preorbital frontal cortex, deeper regions deep in the brain. And of course in some individuals that means that can hijack the pleasure. And after a while, when you become very dependent on these kind of drugs, there's very little pleasure but a lot of wanting, a lot of desire, and you're basically stuck in that one phase where you cannot think of anything but that one drug. So that, I think, is quite interesting. And of course, very interesting as well, given the predicament that we're in with the bankers, is that when you think about the highest reward of all, namely that of money, it's very difficult to be sated on money, unless you actually eat it, which I can't recommend. But if you do that, and you just get people to gamble, not with your own money, because that's what gamblers never do, and certainly not bankers, but if you just gamble, what you find is again that different parts of the orbital frontal cortex is engaged with differences between either tracking with no behavioral consequences or tracking with behavioral consequences. And so with this and with many other experiments, we've tracked the pleasure brain, the kind of underlying mechanisms that are driving our emotions. And it turns out from this drawing from an article I did in Scientific American, you can see how it is that there's almost like a cascade of activity going to the front of the brain, linking all of these various things. And once you then understand how these things work, you can then start to try to change them. You can start to sing the mind electric. And through work with my good friend and colleague, Thibaut Assis, who's a pioneer of deep brain stimulation here, talking to a potential future patient, you can do magnificent things. You can have little girls like this little girl, who's a girl who's got dystonia. Dystonia is a movement disorder which renders her cognitively all there, but she's just been asked to hold her hands out like that and keep steady. And as you can see, she's finding it very, very difficult. She can't hardly stand up, and if nothing is done for this little girl, this would be a little girl who will basically be bound to that wheelchair. Now, if you, like Thibaut would do, would drill 2 holes and target the globus pallidus internal segment, the GPI, and stimulate with 130 hertz and leave her so that she's had a bit of physiotherapy, this is a girl who's got her life back. This is a girl, this is about 10 years ago, who is going to mainstream schooling. The moment the battery, however, is turned off in her chest, she will go back to being what she was before. But it is like a little miracle. And of course, the only reason why we can do this to this little girl is because Thibaut has performed a lot of experiments in other animals, for which he's been very vocal, and like other people here present, like Colin, has been made to pay the price for that. But I think this is the kind of thing that real experimentation in other animals can bring about. And you can even do things that it's very difficult to find good experimental models in other animals, namely pain. So one of the things that Thibaut has pioneered is putting electrodes into, and I'm showing you a little video on the right, to put it into an area deep in the brain called the PAG. When we do that, we can make a pain and a phantom limb that is no longer there, make it disappear. 20 hertz, when we stimulate, the pain goes away completely. We turn it up to 90 hertz, and the pain becomes unbearable. So that's kind of a puzzle. But it's an interesting puzzle, because when we then look at what happens when we scan people while we are turning their pleasure on and off, what we find is that we get activity again in the prefrontal cortex, in the orbital frontal cortex, again showing that this is one of the main parts of our brains that are to do with pleasure and with emotions in general. And then again, working with Annie, we thought about how could we make this a reality? How could we make a sculpture that could be made to actually show pain and pleasure? And in work that Robert has here in his gallery, we made, basically using these imaging techniques, we traced the connections from where we put the electrode in somebody with incurable or treatment-resistant pain, and worked out all the connections from that to the rest of the brain, and that is what that sculpture is all about. And I think it's a sort of it's a complement to the first sculpture that Annie did, the sense. It's basically trying to track that kind of here be dragon space and trying to think about how it is that we relate to these things. And of course, there's no good reason to be relating to chronic pain because there's no good reason for pain. But what about mental pain? What about things like bipolar disorder? Could we come, by understanding emotions, come to treat it in a better way? Here's work from my good friend Peter Wybrow from UCLA, who basically just asked people over, and at the bottom in red you can see a normal person being asked to rate their mood over 50 days. And sometimes they're up, sometimes they're down, but it's sort of fairly steady around a center baseline. You do the same with a bipolar patient, and what you find is that you get some people that are up, manic for some time, they go back to a baseline, then they fall into depression, and they come back up to the manic phase. Now that, to the naked eye, looks completely chaotic, but in fact it's exactly not. In fact, a lower dimensional fractal mathematics is the best way to describe that. And that means that it really is quite a rigid system that is producing that kind of graph. And so just thinking about what it is about in our brains that makes the switch possible, so that even though you're sitting here falling asleep postprandial after having, if there suddenly was a fire alarm, you would all be heading for the exits. Because it's easy for you to switch your brains into the right kind of mode. And the reason why it's easy is because we have these networks that help us reallocate activity. And one of those involves this system. Is called the default mode network, and it involves the orbitofrontal cortex in particular. And thinking about that, we then got quite excited about the possibility of modeling this, to use various abstractions with computer models, thinking about how we could reconnect the brain and run various simulations on top of that. And the kind of mathematics you see there are very simple. This is a coupled Coromoto oscillator, and all it's doing is basically just looking at how it is that these brain region oscillates over time. But with such a simple model, we've been able to show in work that is coming out now and has been coming out for a while, that we can actually model very well what happens, both in terms of the empirical data, which is what I'm showing in the middle, compare that with the model. So in other words, just by running these coupled oscillators in the kind of geography of the normal brain will give us this kind of complexity. And now the big question then becomes, what happens then when the brain is disordered? As it happens, and this is work with Gustavo Deckham from Barcelona, if you think about what the brain is doing when it's in a balanced state, it's actually at the edge of a bifurcation. You are able to either shift to another thing or do something else. But what happens in mental illness is that you're moved further away from that bifurcation. You're suddenly in a much more rigid state. And that's partly to do with the way that your wiring changes. And of course, once the wiring starts changing, once the synapses start changing, then the whole system becomes more rigid and it becomes a lot harder to change. So if you're serious about thinking about mental illness, you could of course stick electrodes in people, and there's been limited success with that, even for depression. But if you're really serious about that, you've got to start somewhere else. And that somewhere else is where my other work really starts. And it starts with this kind of thing. This is a video that you can all access on YouTube. It's called 4 Laughing Babies, good for Monday mornings. It just goes on and on, you know. So, as I say, it's great for Monday mornings. So what is it about early childhood? What is it about growing up in a sink? What is it about seeing the glass as half full rather than half empty? If we're really serious about mental illness, this is where we should start. This is by understanding what it is about parents and about the changes in the child's brain. And in work that I do with Alan Stein in Oxford, we've been taking these kinds of things that we learn from the neuroscience, and I'll show you a little bit about that in a moment, and we've taken them to Africa, to South Africa, to do interventions on mothers and fathers that are postnatally depressed, teaching them how it is that they can interact with these kids to provide the right kind of contingent caregiving that stops them from having half-full lives. Because, of course, the truth is that if you have a parent with any kind of mental illness, but specifically postnatal depression, you're much more likely to suffer from something later on. Now that, of course, is a huge burden on the parent, and it's quite easy to teach how it is that even postnatal depressed patients, how they can pick up on the cues that they don't normally pick up on. And those cues, of course, are the way babies look, the way they sound. And in work that has used this kind of giant hairdryer, which is a new hairdryer that we've got in Oxford recently, which is designed in Finland, which is basically a MEG machine that allows us, unlike the MRI machine that I showed you, to look at what happens over milliseconds in the human brain with very good spatial resolution. We've been interested in seeing what actually happens when you look at these babies. And in work that was published back in 2008, we were able to show that when you look at a baby, which is the left column, and you look at an adult, you find that there's activity about 130 milliseconds in your fusiform face area. The area of your brain that Oliver Sacks very nicely described in his book, The Man Who Mistook His Wife for a Hat. If you lose that area, you can no longer recognize faces. So you get activity in that area when you see a face. And so we thought that when you looked at a baby and if there was something special about the baby, we would sort of expect to see activity much later when you come to evaluate the actual baby's looks. But as it happens, when we did it with this particular scanner, we were able to show that in the medial orbitofrontal cortex, the emotional part of the brain, within 130 milliseconds, which is what I'm showing you with the red blob, if you follow that up here, I don't know, I'm just going to show it to you here. So this is 130 milliseconds, this is the frequency band, and here you can see how there's a lot of activity in between 15 and 20 hertz, even down to 13 hertz, in and around the same time as you recognize a face. So that, and these were all in adults that are not yet parents, suggesting that we all have what Konrad Lorenz called the kinship schema, this thing that we see babies and we can't help but try to protect them. So this is potentially important. This is why we survive as a species, is because we take care of these kids, that we learn how to provide contingent caregiving. And yet, all it takes is for a small deformation of the lip, a cleft lip like that, as you see in the kid on the right, to actually disrupt this whole pattern. So in other work, we recently demonstrated that if you look at that, we find the same kind of response in the fusiform face area, but it's more or less disrupted in, again, adults that are not yet parents when they look at babies with cleft lips. So what we're looking at right now is to see whether we can come up with an intervention where people will focus their attention around the eyes as opposed to around the mouth, and see whether that makes a difference. And whether, in fact, expertise makes a difference. Whether having worked with these babies for a long time will make you actually blind to that. But of course, much remains to be done, and this is just a brief taster of it. Apart from this book, I've also written several other ones. One of them is a pink book called The Pleasure Center, which came out some time ago. And when your colleagues look at that, they say, "Oh, Morten, are you sure that's science?" And then you have to answer them by writing the black book on the right there, which is a magnum opus. And I think the definition of a magnum opus is really something when dropped from third floor can kill a man or a woman. And that's basically all of this kind of scientific details are in there. I thought I'd just show you some of the people that did this work between here in Oxford and Aarhus. And I don't know how we fix for time. Do you want to know a little bit about music? I mean, maybe we should just do a little bit of... I mean, I kept this because I thought there might be some of you interested in music. Music is one of those fantastic pleasures. Steven Pinker, who I admire, I think is a very interesting man, famously wrote, "Music could vanish from our species and the rest of our lifestyle would be virtually unchanged." Now, Steven is a nice guy, but I think he's deluded. And I think just the success that Apple has had with the iPod shows you how deluded he is. Music is probably the most important thing. It could well be a byproduct of who we are, but it certainly is very important. And what better way to look at that and the pleasure of music than to look at what it is about rhythm that makes us dance. So we took this hard-working man in show business and took one of his sort of tunes. Here's an example. So you can hear that's kind of funky, right? And the reason why it's funky, the reason why you want to move, but you're being German about it, is because of the guitars. You can hear how they're syncopated. You can either hear the beat or you can hear just beside the beat. And they're, in that sense, a bit like the Rubens vase. You can either see the face or you can see the vase, but not at the same time. And the amount of syncopation is what makes it rhythmical, what makes you want to dance to it. And so what we did in a series of experiments looking at the rhythm and the importance of how it is that rhythm changes our sense of pleasure, we took the kind of drum beats that you find in funk music, and we made them with a snare and a hi-hat, and we basically just shifted the beat around. Same amount of information in each of these three bits that I'm going to play to you, but it feels very different. This is an example of where we just try to stick closely to the beat. I don't know, it's a bit like a march, right? But not quite a military march, but not something that most people would dance to. Maybe the Germans. But the reason why I make fun of this is because I keep getting invited to Germany to talk about pleasure. Now, some of you may know there's no word in German for pleasure. It's not entirely true. I mean, Kant had a word which was Wohlgefallen. But Wohlgefallen after sex would probably get you a slap. I mean, that's maybe what you want. But so I gave a talk at the Max Planck in Munich, which Kreppelin did all his work and so on. And there were all these professors sitting in the front row, and I played them this music, and they all looked at me like this is not funny. So when they suddenly heard this, one of them started wiggling his toe, and I knew I had them at that point. You can hear that's a lot more funky, right? There's something there, right? Just about shifting the beat. And so you could think that shifting the beat a little bit would make it funky. So if we shifted it a lot, that would probably make it even funkier and even better. So we did that. That becomes like the crouch celebration, right? After he scored a goal. Robot dancing. So there's clearly something about music and something about the way that pleasure relates to music that is U-shaped. You have too little, it's not too good. You have too much, it's not too good, but it's just right. So it's an inverted U-shape. And a lot of pleasure experiments are exactly like that. A little sugar is not too good, just the right amount, but too much, of course, is not very nice. And so doing that, playing these rhythms to people while they were in the scanner or strapped with Wii controllers to the body, allowed us to try to quantify what happens when you experience pleasure of music. And when you do that and you put them in the scanner, what you find is that you get exactly the same kind of relation. You get the auditory cortices saying that you actually get some information into your brain. But once you come to like this, so when you like the beat more than the two other ones, it's your pleasure system which is again is running wild. And so one could in fact take this argument, and recently it has been done by Anjan Chatterjee, saying that when we desire beauty and enjoy art, it's really about the pleasure system. Now sadly, this is a great book about the visual arts, but sadly Anjan hasn't really spoken about music, because I think music is probably the strongest argument we have for why it is that pleasure is important when we engage in art. It's much harder to get people to really emote when they are relating to art on a wall. It's not impossible, but it takes a special kind of person to stand and cry in front of a painting. It doesn't take a very special person to stand and cry if they listen to their favorite music. And in fact, it would only take me maybe 2 or 3 bars of your favorite music to completely change you, to transpose you into another state, that it's very hard to do with the visual arts. Yet, I think the contention and the evidence so far is that the two are almost certainly linked. It just so happens, and I'm sure Colin can speak to that, that we are much better at dealing with our visual world. We're much better at actually putting a wall between ourselves and the kind of visual things. And we really need to do that, especially when you look at the news every night. I mean, we must insulate ourselves from that kind of problem. Anyway, thank you so much for listening.